we need to discuss a little bit of homological algebra. This is not something that one typically encounters in any algebra course. This is specifically the kind of algebra that one needs for doing homology, hence the name homological algebra. So everything that we're about to do today, this is completely algebraic. There's no topology behind what we do. However, the reasons for why we're doing this is because we want to eventually get to topology. Right? We want to be able to use this. So it is convenient to first discuss the algebra first, and then you will see how it gets applied to what we want to do in topology. Now, this might be a little bit abstract. It might be out of nowhere, but you will appreciate it more when we get to the topology. And it is helpful to start with the algebra first, make the definitions a little bit more general, make them a little bit more flexible, and then bring the topology in afterwards. Let's start with the following definition. An abelian sequence is a sequence Now, you should note that my sequence, I start my index at 0. That's often what we do. But the index does not have to begin at 0. And it could also be a finite sequence. So you could have, let's say, a sequence of 5 groups. But I just want to set up the definition like this. So it is a sequence of abelian groups. So every an here is an abelian group, together with, let's say, descending homomorphisms. So you have a homomorphism, let's say Fn, from an to an minus 1. Of course, if you reach the end of the sequence, by the way, you could have an infinite sequence. Like, if you want to, you can even talk about a sequence being indexed by the integers. So it's just that in most cases, our sequences are indexed like this. So it's descending. Of course, if you're at the end of the sequence, if your sequence has an end, that would be a0. And then a negative 1, there is no a negative 1. So you would just interpret. So when you reach a0, the F0 map is just understood to be the map that goes to the 0 group. That would be the 0 group. So that should just be the convention that if it's out of bounds, you just make it the 0 group. So descending homomorphisms. So that's what we call an abelian sequence. And of course, the motivation for this is because when we talk about chain complexes on a topological space, we have a topological space, and then we form this sequence of groups called chains. And we know that there is a homomorphism from an n-dimensional chain to an n-1 dimensional chain, and the homomorphism is what we call the boundary operator. So that's sort of the motivation for this thing called an abelian sequence. And let's denote the whole thing by script A. Okay, so this whole thing is going to be denoted by script A. There is some sloppiness. We get sloppy and omit the FNs. If you want to be a little bit more precise, you would say that script A contains a sequence of groups together with descending homomorphisms from each one, but that's too much to write. So we just get sloppy, we just only write the groups, and it's understood that you have descending homomorphisms. Similar to a topological space, we only write the set, we never write down the topology. It's just understood that it has a topology. Okay, so this is a abelian sequence, and then we say, continuing with our definitions, so let A be an abelian sequence, and B be another abelian sequence. A morphism between two abelian sequences. And this is going to actually be the theme. So I should say this is, we can say this is like the theme for homological algebra. So the theme is everything is obvious. And despite that, it is still hard. So because it's that theme that we have in modern mathematics that we always talk about, that what you need to do is always the obvious thing, right? It's the first thing that comes to mind. But why is it hard? Well, because there's abstractions, there's a lot of definitions. Sometimes it's hard to see the motivation for what we're doing. And so in that sense, it is difficult. But we want to define what a morphism is between two abelian sequences. So it's the obvious thing. So what's the obvious thing? Well, what's an abelian sequence? It's a collection of abelian groups, right? It's a sequence of abelian groups. So a morphism should be a collection. So it is a collection of homomorphisms. So I'm not even going to say homomorphisms because we are talking about groups. So it is a collection of homomorphisms from AN to BN so that the diagram commutes, so that the diagram commutes. So what diagram are we talking about? Well, we have descending homomorphisms on AN. AN plus 1. Then we have BN plus 1, BN, BN minus 1, and so on. And we're talking about on every level, we have a homomorphism. And we want these squares to commute. That's the condition here. I should say that it's very common in homological algebra to not even put the names on these arrows. You can often figure it out from context. But these, of course, would be like FNs, and these would be FN primes. These will be like maybe GNs. But it's better to probably leave out the name of those arrows unless you really need to, unless you want to be more precise about what you're saying. So that's a morphism. So basically, we constructed a category of, let's call these abelian sequences, right? So this is the category of abelian sequences. This is not the category of abelian groups, it's the category of abelian sequences. So we have our objects in this category, and the object in this category is, abelian sequences, and morphisms between two objects is a collection of homomorphisms that make the diagram commute. And anytime we have a category, as we said, it's always a good idea to think about initial and terminal objects. So the initial and terminal objects are the same. And it is just the sequence of zero groups with zero morphisms, right? So that's the initial object. It is a sequence of zero groups. So here's some terminology. So if the initial and terminal object is the same in a category, it is sometimes, I want to be a little bit careful. There might be some extra conditions, so I want to be a little bit, but sometimes, usually, it is sometimes called the zero object. The zero object. Okay, so the zero object would be this, and it is denoted by our favorite math symbol, which is the number 0. So 0 means a lot in math. So here it's the zero object in the sequence of abelian sequences, right? It's the zero object in the category of abelian sequences, and it is the group of zeros indexed by the number 0. So that's quite a lot of zeros, but they all have different meanings, and yet somehow we can distinguish them. It's kind of similar, like the difference between 0 as a number and 0 as a function. But we understand, like we write 0, but we understand the difference. Or we write like 0 as a vector and things like that. So the probably most overused symbol in all of mathematics, the number 0. So we just denote it by 0. Just to get a bit off topic, an abelian category. So you probably one day will hear this thrown around, abelian category, as opposed to a category. So an abelian category is a category with a zero object plus something else, right? Which I do not want to get into. It's a bit more complicated. There's some conditions about products, co-products, and then more generally limits, co-limits. So I don't want to get into it, but let's just say that usually that, right? You have the zero object, you say it's an abelian category. There's some extra details we're not going to get into. So this would be an abelian category. By the way, topological spaces are not an abelian category because we talked about initial and terminal objects and we saw they were not the same. So, okay, so we've just constructed a category. So the next thing that I would like to talk about are what is known as chain complexes. Definition. So this is an abelian sequence, is called a chain complex if and only if, and you can probably guess what this means. So you have a descending homomorphism going to an, you have a descending homomorphism going down to an minus 1. Again, assuming we're not at the end of that. If we're at the end, then there's nothing to really check. And we want this composition to be 0. And look at that, the number 0 again. This is the 0, that's the 0 homomorphism. So if you really want to write it out, this would be Fn plus 1, that's the descending map. This is Fn, that's the descending map. And you're saying if you do Fn plus 1 composed with Fn, that should be equal to the 0 map. This, of course, is motivated by what we do in topology, because in topology, these groups are what we call the chains, and the homomorphisms are the boundary maps, and when they're composed twice, they give you 0. And that's how we get homology. So in this case, we can define, well, actually, before I do anything, in this case, the kernel, the image of the incoming map into an has to be contained in the kernel of the outgoing map, right? This one is contained in that one. And the reason for this is very simple. We talked about this before, because if you take something in an and you apply f to it, you end up over here. If you apply f again, you get 0, right? So if you take something in an, you map it over there, whatever you get, when you apply f again, you go 0. So the image is contained in the kernel. So this is a subgroup of that. And hence, we can define its homology. So we would say that the nth homology of this abelian sequence at level n, so you have homology at every level, at every dimension, you would then say that this is equal to, by definition, this is exactly how we do it for a topological space. You would just do the kernel mod the image. So of course, the kernel of this one modded out by the image of that one. Of course, the image is a normal subgroup of that because these are abelian groups. There's nothing to check about normality. And you get a group, and that quotient group that you get, it's called the homology group. So that's what we call a chain complex. If your abelian sequence is not a chain complex, then this makes no sense, right? Then you cannot talk about homology. The next thing I want to say is, so there, as you can see, this is kind of boring. Maybe you're one of those people which find this interesting, but some people would say that this is kind of boring. Without any context, this is not very interesting. But when you put it to use for the purposes of topology, then it does certainly become a lot more interesting. But by itself, it's not exactly, one can argue, the most exciting area of mathematics. But it's necessary, right? It's what we call a necessary evil. You need to discuss this in order to understand some of the ideas in topology that go further. So the next definition is, we're going to say that, let's say A is, again, an abelian sequence. And we say that this abelian sequence is exact, right? It's an exact sequence, right? An exact sequence. If and only if. So you see, in a chain complex, the images are contained in the kernel. But here, the image of the incoming map is actually exactly equal to the kernel of the outgoing map. Hence the name exact, right? They're exactly equal. So in this case, the nth homology of an exact sequence would be equal to 0 at every level. So this is the 0 group because, right, you're just modding out by the same thing. That would just be the 0 group. So there's actually an interesting, I had a professor once who actually took, I think he met with Grothendieck, and he heard this point of view from Grothendieck. It's not really relevant for what we're doing, but I think it's interesting. So this is Grothendieck's point of view. Now, my professor told me this about cohomology, but I imagine you can probably do the same thing with homology. And Grothendieck's point of view was that homology, so he said this about cohomology, but homology is a measure of exactness. It measures how close an abelian sequence is to being exact. That's what it's supposed to measure. It's a measurement of exactness. So it's just an interesting way, right? So if something is exact, homology gives you 0, and if it's not exact, then the kernel, that ratio, that quotient, it puts some kind of assignment to how close it is to being exact. Maybe it is exact at certain positions, but not at all of the positions. And what I want to do next is I want to give you some examples of exact sequences that commonly occur. So there's going to be examples of, and these are going to be finite exact sequences. So as I indicated earlier, when we talk about an abelian sequence, we do not need it to be indexed by non-negative integers. You could be more general. You can just talk about like a finite sequence. So here's some examples. So the first example is you have 3 groups, 0, A, and B. So maybe if you prefer, maybe you call this one A0. Actually, maybe you should call this one A2. You call this one A1, and you call that A0. And then you have this indexing AN, where n is between 0 and 2. Okay, so you have a finite, right? You have a finite list of groups. So the one at the beginning is what you're calling A2, then you have A1. So they're descending, they're going down. But we do not even bother to kind of write it like that. We sort of just write it like this. This is, of course, the zero group, the 0 abelian group. And this map is obviously the 0 map, right? That's the only map you can have. And then you have some kind of mapping over here, F, which again, often we do not write this. But in this case, so when you have 0 on the left, so this sequence is exact. So in order for you to check that it's exact, you have to check that it's exact at this position, because there is no incoming map here. There's no incoming map, and there's no outgoing map. So this is the only position to check is exact, i.e., if the image of the incoming map is equal to the kernel of the outgoing map, if and only if. Now, think about this. The image of the incoming map is 0, right? 0 gets mapped to 0. So that means the kernel of the outgoing map is 0. So that means this kernel is 0. This is another way of saying this is an injection. If and only if A into B is injective. So if you want to be really fancy in algebra, instead of writing A into B and then saying is injective, you can show off and you can just write A into B, put the 0 on the left, and then say exact sequence. It's the same thing. Then you can also have a 0 on the right. So you would say A into B into 0 is exact, and you can check this if and only if the map from A to B is surjective. The third thing that I want to then bring up is you can also have a situation where you have a 0 on the left and right. So this is exact if and only if the map from A to B is an isomorphism. So if you want to say something is an isomorphism, you just put 2 zeros on the left and you say it's an exact sequence, because in this case, the right part of it tells you it's surjective and the left part of it tells you it's injective. So that's how you get an isomorphism. Now, another situation that appears is when you have three different groups with two zeros on the left. So you have 0 into A, into B, into C, into 0. So you have a situation like this. So this sequence is exact. This actually has a name. This comes up so much in homological algebra that we give it a name. This is called a short exact sequence. So a short exact sequence is specifically a situation when you have three groups in the middle and you have two zeros on the left. Okay, so I'm not sure if this one has a name. Maybe it does, but this is not called short exact. This one is not called, neither is this. It's specifically this one. This one appears so much in homological algebra, we give it a name. This is called a short exact sequence. So we say that that sequence is exact, right? It would be exact if and only if the map from A into B is injective. The map from B into C is surjective. Okay, so this is just coming from before. The reason why this map is injective is because you sort of just focus on that block. If you focus on this block, you get that that is surjective, and you get the exactness at B, and the image of the incoming map from A into B has to equal the kernel of the outgoing map from B to C. So that's called a short exact sequence. The next thing that I want to say, you can say this is example 5. This is common, you can say common ways. This is like a common way you get a short exact sequence. And if you go 0 into A, and here you have B, and the one in the middle is the direct sum or the direct product, depending which one you want. It's the same thing. In this case, you only have two groups. And this is the obvious map, right? This is algebra, homological algebra. The maps are always obvious. What's the obvious way of mapping this element to that element? Well, it's just, you would just take x, and you would map it to x comma 0. And then what's the obvious way of mapping an element over here into B? Well, you would take an element xy, and you would just map it to the second coordinate. And it's easy to see that this is, of course, injective because different x go to different pairs. This is surjective because anything in y, you can find something that projects to it. Then, so injective, that's surjective. And then it's easy to see that if you go in and then you project to the 0 coordinate, you end up getting 0. So yeah, and if the image is equal to the kernel, if something gets mapped to 0, it means y had to be 0, and then you can find, and then this is an x, and then you can find something in A that gets mapped to it. So it's very easy to check that this is indeed a short exact sequence, right? This is a, so this is short exact sequence. The next one that I want to say is, this is another common one. So if A is contained in B, so you have a subgroup, then we get a short exact sequence of the following type. You have A over here, then you put B, and what map is that? That's the obvious map. That's just the inclusion. That's just the inclusion of A into B. And here you're going to put this is what you call the co-kernel. It's just B mod A. This would be B mod A. That's you can do A mod B because that's just the quotient group. And you can check, it's not difficult to see, that this is, again, a short exact sequence. So this is another common one that appears where you introduce a quotient. Now, the other thing I wanted to say is, suppose you have a short exact sequence. Let's say we do it like this, let's say. I'm specifically putting the C in the middle. Is it true actually, let me do it like this. What about the converse the converse of observation 4 and observation 6. In other words, so let's say I have a short exact sequence, A, B, C. So I'll write it like this, short exact sequence. Is it true that the one in the middle, so you see the one in the middle is isomorphic, well, it's the direct sum of these two. Is it true that the one in the middle, B, is isomorphic to a direct sum of the two ones on the outside? And then you can also ask, so this would be the converse to observation 5. What's the converse to observation 6? So if you have, let's say, a sequence like that, is it true that the one on the right, C, is isomorphic to B mod A? And so those are like the converse statements. So I'm going to begin with the easy one. Okay, so the second question, this is the easy question, and the first question, that's like the hard question. So the easy one, is true in the sense that it's true because, right, okay, because if you have a homomorphism F, let's say from B into C, then if you take B mod the kernel of the homomorphism, it's going to be isomorphic to the image of B. Right, this is what you call like the first isomorphism theorem in algebra, that anytime you have a homomorphism between two groups, you get an isomorphism between the quotient with the kernel and the image, right? To kind of use that a lot in algebra. This is like very easy to show, right? You use that a lot in algebra. And that's exactly what's going on over here, because f of B, that's exactly C, right? Because the group is, I'm sorry, not the group. This mapping is a surjective mapping, so this is C. And the kernel, well, the kernel, this is B mod the image of F, because we're assuming it's exact, okay? So that's the image of A. But in a way, this is a little bit sloppy to say. You cannot say B mod A, but you can be sloppy and you can just say that this is B mod A. And the reason for this is because A is an inclusion, right? There's an inclusion, so you can abuse notation and say that A is a subset of B. And then based on that observation, you're seeing that the one on the right is then the quotient of these two, right? So this example, you see, we have these two examples of short exact sequences. Example number 5 is when you introduce the quotient on the right. And what we're seeing over here is that this is really the only example you have. Like the only example that you can have a short exact sequence is when the C is the quotient of those two. But what about 5, where the one in the middle is the direct sum of those two? This is the reason why this is hard. So the hard one is not always true and depends on what kind of group C is. Or even more difficult, even more difficult, what kind of group A is. So there is no, so you kind of learn about this in, it has something to do with, so for those of you who are interested, there's these things called projective and injective modules, which we're not going to go there. We do not want to overcomplicate this class. That's something from commutative algebra. I do not want to go there, but I'll just say this. So projective modules are easier to describe than injective modules. And I'll just say this, that if C is a free abelian group, then this converse that we're asking is true. So in other words, what I'm saying is, if you go back to the sequence over here, if this sequence is short exact, and you happen to know that C is a free abelian group, so that means it's isomorphic to Z to the n, just assume it has finite rank to make it easier, then it's necessarily the case that the one in the middle is isomorphic to the direct sum of those two. And I'll put it on the homework and you'll get to prove it, but it's not true in general. In general, it's true when C is something known as a projective module, but let's not go there. The one with the A is even more complicated. So I think that should be good enough. In case you're interested, for the one on the A, it needs to be something known as a divisible group. Divisible group means you can divide things. So something like Q or R. If this is Q or R, then it's going to be true. But let's not even bother to go there. Okay, so that's a little bit of stuff on exact sequences. And now I want to talk about exact sequences consisting of chain complexes. Let's start with this definition. Let A, so this is going to be an abelian sequence. And if you want, you can assume that these are also chain complexes, because that's what we're going to be working with anyway. But these could be abelian sequences more generally. Be abelian sequences. So in particular, it means that they come equipped with descending homomorphisms that we do not bother to write out. A short exact sequence of abelian sequences, so it's going to go like this. This, let me remind you, this is the zero object. So this would just be the sequence of zero groups, but we just write zero. That's the zero object in the category of abelian sequences. And you have to recall what a morphism between abelian sequences is. A morphism is a collection, right? So this is a sequence, this is a sequence. So a morphism between script A and script B would be a collection of group homomorphisms on every level that commute with the diagram. So a short exact sequence of something like this is short exact at every level. In other words, if you have, so on level n, you would have this. AN, BN, CN. And this is going to be a short exact sequence of abelian groups. And it's also short exact on the previous level. Well, I should say on the level above it. So this collection of homomorphisms, they create short exact sequences at each level. Furthermore, because these are homomorphisms, they will commute with the descending maps. So we have descending, and maybe I should also write it down here, AN minus 1, BN minus 1, CN minus 1, like this. So when you go across the rows, you have short exact sequences, but when you go down the columns like this, you can also go down, because the columns are coming from the descending homomorphisms, which we have, and all of these squares are going to commute, because that's what it means to be a morphism of abelian sequences. Okay, so the rows are going to be short exact, and every diagram commutes. So this is what it means to be a short exact sequence of abelian sequences. And as I indicated, you could assume, if you want to, you can also assume that these are chain complexes, because that's what we're going to be applying it for. So now that we understand this definition, we're going to get to a lemma in homological algebra, which is used a lot. And this is called the zigzag lemma. It's also sometimes called the snake lemma. But the snake lemma is really a generalization of that. It's more general than the zigzag lemma. And this is the way it goes. Let A, B, and C be, instead of abelian sequences, we're going to be, they will actually be chain complexes. So by a chain complex, we mean that if you compose two of these descending homomorphisms together, then you get the zero map. And the theorem says a short exact sequence of chain complexes. So let me remove this. So a short exact sequence of chain complexes induces. So again, induces means you're using one type of structure to create a new type of structure. So it induces an exact sequence in their homology. And here's that sequence. So because these are chain complexes, we can talk about the homology of each one of these. So one has the homology of A, the homology of B, the homology of C, and then, so you see it kind of goes like A, B, C, but then when you reach C, you circle back to A again, but the degree goes down. So that would be Hn minus 1A, Hn minus 1B, and so on. And then here you would have Hn plus 1C, H plus 1B, and so on. Of course, if at some point you run out of room, it just becomes zero at the end. So this is what we call the zigzag lemma. So if you have a short exact sequence of chain complexes, then you can use that short exact sequence to create an exact sequence in their homology that goes like that. And the proof of this is actually kind of interesting. So the proof, it's actually a triviality. It's a triviality, and it uses something called diagram chasing. So the proof is very mechanical, but the proof is tedious. And instead of me writing out the complete proof, instead I'm just going to show you parts of the proof, and then you can do other parts of the proof. So the first thing that we need to do is we need to explain how these homomorphisms are being defined. Because I'm not telling you how they're being defined. I'm just saying it is possible to define them and get an exact sequence out of that. So you first have to define all of these homomorphisms. And then after you define the homomorphisms, you have to show that this sequence that you get, so this will be a sequence of abelian groups, that the sequence that you get will be an exact sequence. So that would mean that at every one of these groups, the image of the incoming map will be equal to the kernel of the outgoing map. So that's what you would have to check. So let me begin by first showing you how the homomorphisms are being defined. And then we can talk about why the sequence is exact. So again, this is, as you will see, this is very tedious. There are going to be a lot of things to do, but every one of the things that you need to check will be trivial. Like there's absolutely nothing clever in what we're about to happen. Everything just follows automatically. So here's how this works. So, and again, as I said, at the moment, it's not clear why we even are talking about that. But after we discuss the zigzag lemma, we're then going to return back to topology, and then you will appreciate what we're doing a lot more. Okay, so here's the way we're going to start with this. So let's just write it out on the nth level. So we have H, so we have 0, AN, BN, CN, like this. And then we have something above it, AN plus 1, BN plus 1, CN plus 1, and we have something below it. So I'm going to show you how to define. I'm going to show you how to define. I'm going to highlight this. So let's talk about how this one is being defined. So I'm going to pick a part of this sequence, let's say this one, and I'm going to show you how to define that one. And once you see how that one is defined, the one from, and then the same kind of argument can be applied from A to B on this level. And then from there, it will be clear how to do it from B to C. Okay, so let's just first explain how that arrow is being defined. And what I'm saying is you're going to be using this diagram to define that homomorphism between the homology groups. So we have this, but you also have to understand that these are abelian sequences, so we have descending homomorphisms like this. They're going down, like that, going down. And by the way, if you want to, you can also make the zeros go down, but they're not really going to do anything for you. I mean, you're not going to be using the zeros for this part of the argument. If you want to, if it makes you happy that you technically do have maps going down, you can write them down. We're just not going to be using it. So this is the kind of diagram that we have. And now we want to define, we want to go. So the question here is, how do you define the map from this one to this one? So here you have to recall what homology is. So this, by definition, this is you can say the group of n cycles. Okay, and this is the group of n cycles. So these are n cycles in script A, and these are going to be n cycles in script B. Now, what is a cycle? A cycle, an n cycle, is by definition an element of an that has boundary 0. So that means it's something, so bound in this case, now we're not talking about boundary as in topology, we're being more abstract, but the idea is you have that homomorphism, so it's something that maps to 0, right? It's something in the kernel of that map. So that would be what the homology is. And it's technically not n cycles, it's the group of homology classes of n cycles. So it's going to be homology classes. But I think it's just easier to write it out like this. So in order to define this map, you have to pick some cycle. So let's call this cycle, let's call it X. So for lack of a better name, let's just call it X. So X is going to be a representative. We will obviously have to show that what we're going to be doing is well defined. Okay, but for now, let's pick a representative for some n cycle. So if it's an n cycle, then that means by definition, it's located in an, right? This representative is in an. So this representative is right over here. And by definition, if it's a cycle, it means it gets mapped to 0. So X gets mapped to 0 like this. And now you want something, an n cycle in B, right? So you need to find something in Bn that's going to be a cycle. So how do you go to Bn? Well, you already have that arrow. So you just take the X and you map it into Bn, and you get something, let's call it Y, okay? And whatever you end up getting, that's the way you're going to, that's going to be the cycle in script B. But there's questions that arise. So the first question that arises is, how do we actually know that this Y is a cycle? I mean, it's true it's in Bn, but we have to check that it's a cycle. So to check that it's a cycle, you have to verify that this Y goes to 0. Well, we know that 0 goes to 0 because the group homomorphisms always send the 0 object to 0. So that one goes to 0. Right? This lower one sends 0 to 0. And because this diagram commutes, right, going like this and going like that is the same thing. And so it means that Y goes to 0. So that means that Y is indeed an n cycle. But, okay, it maps an n cycle to an n cycle, but you're choosing a representative. Okay, you're choosing a representative. What if you have a different representative? So what if you have x prime, right? You have two. So x and x prime are in the same, they're different cycles, but they're homologous to each other. That means their difference is a boundary, right? It's the boundary of something of one higher dimension. So then that means you get another element here, y prime. And you need to show that these are homologous with respect to script B. So we need to show it's well defined. So how do we do that? Well, here's the way we do it. So we do know, so we at least we know these are cycles, okay? So we have an x, and we have an x prime, and we have a y, and we have a y prime. So what do we know? we know that if you do x minus x prime, it is the boundary of something, let's call it z, where z is in an plus 1. So that's just the definition of what it means for two cycles to be homologous. If their difference comes from the previous group. So I'm writing over here the boundary map because that's the way we're used to when we're doing homology, right? That's the way we do it in topological spaces. But it's just whatever the name of that map is. So maybe we'll call that map. Maybe I'll do something else. Maybe I'll call that map. Yeah, let's call that map F. Okay, let's call that map. Actually, let's call that map A. Okay, how about that? We call that map A. So there's something in an plus 1, so that A of z will give you the difference. Now, we have a map going like this from A to B. Let's call this map F. And then we have a map from Bn plus 1 to Bn, so let's call that map B. So let's observe that if you do, and then we have a map, maybe we call that one G, like this. So we know, because the diagram commutes, we know that if we do A composed G, that's the same thing as B composed F. Okay, going like this is the same thing as going like that. So now we have x minus x prime is equal to A this. So let's take this equation and let's apply this map G to both sides. So G of x minus x prime is equal to G of A of z. So this is G of x minus G of x prime, because G is a homomorphism, it distributes over sums. And now G composed A is B composed F. So that's B of F of A. I'm sorry, F of z. Now, G of x is by definition y, and G of x prime, that's by definition y prime. So y minus y prime is equal to B of something, let's call it W. F of z is, let's say, W, so F applied to z, that's something W. So look at what you've proven. You have proven that these two cycles, so we know that they're cycles, and these two cycles in script B, their difference is the boundary, right? It's the descending homomorphism of a previous element of 1 degree higher. So that means that y and y prime are homologous. So there you go. Okay. So this is indeed well defined, right? This is indeed, so this is a well-defined map. It takes you from homology classes in script A, and it takes you to homology classes in script B. So that's how the mapping is defined. Okay, so that's what I mean by diagnosing. You just keep around moving in this diagram and making all of these checks. So the next question that comes up is this a homomorphism? So we have a mapping, we have a well-defined mapping, but is this indeed a homomorphism between groups? So let's just remove this so it does not get in the way anymore. So is this a homomorphism between groups? So we have to pick, let's say, two elements over here, x1 and x2, and we have to basically show that, let's say, x1 gets mapped to y1, x2 gets mapped to y2. Is it true that x1 plus x2 gets mapped to y1 plus y2? Is that true? And this one is actually very easy to check. Now that you know it is well defined, it is automatically a homomorphism, because this is a homomorphism. So if you have x1 and x2, if you were to add them together, then their images will be the sum of the images in that one. So that one just comes from the fact that this one is a homomorphism. So that one was actually kind of easy. So look at that. We have defined this map from here to here, right? We have defined that one. And then you have another one that you have to check, right? There's another one that you have to check. So the other one is, now the one from Bn to Cn will actually be defined in a very similar way. So if you want to go from the homology, if you want to go from the n cycles of B to the n cycles of C, then the way you would do this is actually very, very simple. It's the same exact procedure. If you pick an n cycle in script B, then that would be an element in Bn. That's a cycle, right? That maps to 0. And then you just use this arrow that will send it over to Cn, and then you can show by the same kind of reasoning that what you get in Cn is going to be a cycle in script C. and then you show it's well defined, then you have defined that one. So let me just now highlight the ones that we can do. We can define that one, we can define that arrow, we can define this arrow, we can define that arrow, and we can define this arrow, and so on. Because you see, going from A to B, we have an arrow. Going from B to C, we have an arrow. But the one which is a bit concerning is, how do you go from C back to A? Because we do not have an arrow from C to A. So how do we do this? So this is why it's called the zigzag lemma. So that's the terminology. The idea is, so let's, I'm going to highlight the one we want to focus on. So let's focus on this one. We want to define the arrow from the homology of script C to the n-1 homology of script A, and explain how to do it. So it's going to be the same procedure as before. You're going to pick a cycle. You're going to pick a cycle in script C. So by definition, that's an element in Cn. Okay, this is a representative, right? You're going to choose, you do it by choosing a representative, and then you have to, of course, show it's well defined. So you choose a representative, so that's your representative. And where do you want to end up? You want to end up in the n-1 homology of A. So that means you have to end up in a cycle, in the n-1 degree cycle. So that would be an element in AN. So you have to somehow go from this one to that one. Right, so that's why it's so okay. So this is the reason why it's called the zigzag lemma, because the way this sequence up here, the way you construct that sequence is you're basically doing this. You go from A to B, then you go from B to C, then from Cn+1 you go back to A, back to B, back to C, and then you zigzag across like this. So that's why it gets the name the zigzag lemma. Let me remove those arrows. They're going to be way too confusing. So now, how do you end up in that one? So the way to do it is, well, I want to end up over here. Here's what I know. This is something in the homology. So by definition, it means x gets mapped to 0. Okay, so x gets mapped to 0. Right? It maps to 0. Now, this arrow, you see this arrow over here? This arrow is a surjective map. Why is it surjective? Because this sequence is a short exact sequence. It's short exact. So that means that this arrow is a surjective map. As we talked about previously, when you have a short exact sequence, the map from the middle to the one on the outside has to be surjective. So in particular, it means that you can find something in Bn that gets mapped to x. So you can find something here, let's call it y, that gets mapped to x. Okay. Now, this y can be mapped down to Bn-1. So maybe if I write it, I think it might be a good idea to write it over here in words. So you pick x in Cn, since x, and this is the way, well, yeah, pick, so you're going to pick y in Bn so that y maps to x. Right, this is just the fact that this is surjective. Now y gets mapped to Bn-1, right? The y gets mapped here, so that would be z. Let's call this one z. Now let z be the image of y in Bn-1, right? You just take that descending homomorphism and you're down here. Now you want to be able to pull it back, right? You want to be able to say, you can pull back the z. But the problem is, how do you know that there is something in An that gets mapped to z? So this is where you're going to use the fact that this is a short exact sequence again. So you're going to behold, this is like the key idea, z in Bn-1 maps to 0 in Cn-1. Right? Z gets mapped to 0. Now the reason why we know that z maps to 0 is because the diagram commutes. Right? So z gets mapped to 0. So in particular, z is in the kernel, but the kernel is equal to the image, i.e. there is something, let's call it W in A n minus 1, so that W maps to Z. So there's a W over here that maps to Z. So we're going to call this one X. I'm sorry, not X, let's call it W. And the one that you really care about is you just care about this, but this is the one that you care about. And this is the way X gets mapped to this one. So when you do this procedure, so this is the way you do. You pull it back to Bn, you descend down, and then you pull it back to An. That's the way you do it, right? You kind of zigzag across from right to left. And the element, the chain that you end up with, the An minus 1 chain, that's the one that is going to be W. But now you have a lot of things to check, right? That's why I say it's trivial. It's the diagram forces everything, but there's a lot of things to check. So the first thing you have to check is there's a lot of choices. So first of all, there's a choice on the representative for X, because this is the homology class. Let's get back to that later. There's a choice on this Y, because this arrow, it's surjective, so you're picking a Y. So if you choose, what if you have a different Y? So you bring it down here. And then the Z that you have down here, when you pull it back, so we argued that you could pull it back. So when you do pull it back, you're making a choice. So you therefore have to show that this is well defined. So even though you basically have to argue, you need to argue that even though you have choices, those choices might lead to a different W in the end, but all those different W's are in the same homology class. So that's what you have to do. Another thing that you have to actually show is, how do you even know that this W is a cycle, right? You have to actually argue that it goes to 0. Like, how would you know that? So, and the reason for this, so maybe I'll give you an argument. I mean, I do not have space to write it out. And like I said, this is tedious. I'm not going to check every single little claim because it's not very exciting. It's just the main idea that we care about, that the fact that you can do this. But let me at least show you why this has to be a cycle, that this goes to 0. So the reason for this has to do with Y maps to Z, and Z has to therefore map to 0. Why? Because this is a chain complex. If you compose twice, it becomes 0. So Y becomes Z, and then Z has to become 0 because you're sort of applying the arrow operator twice. It's a chain complex. It becomes 0. So whatever that W is, it has to be something that therefore goes to 0. But keep in mind that this mapping is an injection. So if something goes to 0, it has to be 0 itself. So W must map to 0. So in particular, W has to be a cycle. So you've actually shown it's a cycle, but then you have to show that the choices do not matter. Okay? And once you do that, you have defined this map. And then you have to show it's actually a group homomorphism. Okay? So that's what you have to do. So like I said, very tedious, but very straightforward. So this now defines for us the remaining maps from C to A, and so on. But then there's another question that comes up. And the other question that comes up is exactness. Why is it exact? What makes it exact? You have to show that the image of the incoming map is equal to the kernel of the outgoing map. And you kind of do the whole thing all over again. So maybe I'll just do one of these. Again, the key idea is that this is a triviality. There's nothing, really nothing clever about this. It's just unbelievably tedious. So let's focus on this one. Okay, so we want to show to show that actually, that made no sense, what I just wrote. Let's do this one. So we're going to check, actually, that's not, we want to show that the image of the incoming map that goes into this one is equal to the kernel of the outgoing map to that one. So that's what we want to argue for exactness. And so we have to show it's exact at A, at B, and at C. So I picked B, I picked the easy one. You see, I picked the easy one because I have to stay way away from that zigzag one. But you can think about the more difficult one where you have that zigzagging map being used. So these ones do not use the zigzagging map. So I'm making it a little bit easier for myself and leave you with the hard work. Not that it's much more difficult, but you should try doing it. So, and then for every single one of these, you're not going to show it's equal to. It's going to be more tedious than that. You're going to show that one of them is contained like that, and then you have to show it's contained like that. So, yeah. So maybe I'll just do that one. Okay. I think after I do that one, you hopefully will get the point of all of this. You'll get the point of how this works. So the image of the incoming map. So let's say we picked something in this one. So we pick a representative. So we're going to pick this is homology, so we pick a representative. So we pick X, okay? That's a representative. And what do we know about X? This X, the image, right? The image, if this is in the image, by definition, there's something here that gets mapped to it, right? So there's something here, there's a Y that gets mapped to it. And we have to show that if the X comes from the Y, then the X gets mapped to 0, right? So going back to this diagram, if X is in the homology class, it means it's in this one. And if Y goes to that one, that means the Y is located here. And what do we want to show? We want to show that X gets mapped to 0, right? It gets mapped to the, well, this just follows from the fact that this is a short exact sequence, right? This is it's exact on this level. So the X comes from Y, so if you go twice, it therefore goes to 0. And so X gets mapped to 0, right? It gets mapped to 0. So you have shown that this X, so an element in the image is contained in the kernel. Now we're going to apply the zigzag lemma to get something that is known as the Meyer-Vittorius sequence. And this Meyer-Vittorius sequence is what we're going to be using to help us compute homology of a topological space. Now, to do this, what we need is we need to define a sequence of abelian groups, the A, B, and C. So for A, well, maybe I should give you a quick setup to how this is going to work. We're going to assume that a topological space is a union of two open sets. So that's going to be the assumption. And what we're about to do should be a little bit reminiscent of the Seifert-von Kampen theorem, if you happen to be familiar with that. If you're not, then it does not matter. But if you happen to know the Seifert-von Kampen theorem, then we're doing something very similar. We are decomposing our topological space as two open sets. And the idea is going to be basically this: we want homology of X. And what we will have is we know homology of U, V, and how they intersect. So if we happen to know the homology of the open sets that cover X and the homology of their intersection, then we can use that information to help us find the homology of X. So you're basically decomposing your problem into two smaller pieces, and then you're solving the global problem from gluing together the information on the smaller pieces. So that's sort of the idea of what we're trying to do. And we're going to put all of that information into something that is going to be called the Meyer-Vittoris. Maybe we can even say the Meyer-Vittoris exact sequence. It's going to be an exact sequence because that's what the zigzag lemma is going to give us. And the setup is going to be that we need to define our sequence of abelian groups. So the A group, this is the one that's going to take the intersection. So this is going to be the chains in C in U intersect V. So those are the chains. So this is a topological space. By the way, it is okay if the intersection is empty. These will just be the zero groups. So you can still make all of this work out even if the intersection is empty. But then what you're basically saying is you're saying that a topological space will decompose as a sum of non-overlapping open sets. So in other words, these are sort of like the path components of X if these happen to be path connected. So it's not really that helpful, but you can still do it. And the B, this is the way we're going to get B. So the B is going to come from U and V individually. So this one would be Cn of U, direct sum Cn of V. And, well, I should say that anytime you write down an abelian sequence, we always have to indicate the descending homomorphisms. Here, the descending homomorphisms are just the boundary operators on the intersection. So that would mean that A is an abelian sequence, and furthermore, it forms a chain complex. So this would be a chain complex. Well, what about B? Well, how does one define the descending homomorphisms? Well, you basically, so this is algebra, so it's always the obvious thing to do. So let's just briefly write it out over here. There's certainly a descending homomorphism from Cn of U to Cn minus 1 of U. And there's a descending homomorphism on V. This is just the two different boundary operators. And so if you want to descend from the direct sum to the direct sum, you just do component by component. So it's the obvious thing. And then you can check, of course, that that will give you indeed a homomorphism, and it forms a chain complex. So that's the way one would define it on this one. And then you have C over here. And for C, this would be the chain complex that one gets for X itself. But we're going to modify this a little bit. So I'm going to write it like this. So this is going to be Cn. And we're going to put a little decoration here. I'll write it U comma V of X. And I'll explain what that means. So what this is going to be, so it's not all of the chains. It's a very special collection of chains. So where C U V of X, this is going to be the free abelian group generated by all simplices, so all of these maps from the n simplex into X, so that the image of a simplex is contained in U, or it's completely contained in V. So that's the distinction. Whereas Cn of X, these are all simplices from Cn into X. Of course, when I say all simplices, I of course am being sloppy here. I mean the free abelian group generated by all of these simplices. Whereas these ones are being restricted. And the restriction here is you have to make sure that every simplex is being mapped into U or V. So the picture here is, imagine that this is U, and then this is V, and that's how they intersect. And then, like if I pick, like let's say a single simplex, when you talk about a chain in X, you allow, for instance, let's say this is like a simplex that overpours, it spills over into U and V. Whereas in this restricted chain, so these are chains that are being restricted, so it falls into one of these two, you will have the requirement that maybe you have something like this, You can see the simplex, the image of the simplex is sitting inside U, or maybe it's on the other side. Maybe it would be over here. That would be fine. It could be in both, but it's important that it is in at least one of them. So that's the distinction here, that this is a subgroup, right? This one is contained. That is a subgroup of that one. So these are going to be restricted simplices. And the boundary operator, well, it's exactly what you think it is. It's just a boundary operator that's applied in the usual sense. So there's a very simple way of getting from, let's say, a group at level n to a group at level n minus 1. And you just use the regular boundary operator, because if you have a simplex, and the simplex is, let's say, completely sitting inside U, then its boundary is also already sitting inside U. So the boundary operator will then give you an n minus 1 chain that's sitting inside U. So the boundary operator will properly restrict, and it will give you a descending homomorphism, and this will also be a chain complex. So these are chain complexes. Okay, so these are chain complexes. Yeah, so these are going to be chain complexes, and what we will do next is we're going to define a short exact sequence. Okay, so to apply the zigzag sequence, we need to construct a short exact sequence between A, B, and C. So between these three abelian sequences. So so we're going to have our short exact sequence is going to go like this. So we have to define how A gets mapped into B, how B gets mapped into C. So that's why, and then we also have to verify that it is indeed an exact sequence. So A getting mapped into B, well, there's an obvious way of mapping A into B, and it has to do with this. So to define a morphism from A into B, we need to define a map from the nth group. So the nth group will be from this one, Cn U intersect V, into Cn of U plus Cn of V. And this is going to be the diagonal map. So you have to pick a simplex, sigma. So in order, this is the free abelian group generated by all simplices. Technically maps of simplices, but we just say simplices. So you pick a simplex. So it's sufficient to define what it does on the simplex. Well, you have to realize that if you have a simplex, if it's in the intersection, then it's both in U and in V. So you just map it into, you can just map it into itself. So it's just a comma sigma. So this is a diagonal map, okay? And clearly this is an injection. This map is injective. That's going to be an injective mapping. So we have defined a morphism from A into B because we have defined what it does on every level, and these mappings are injective on every level. So that's why we put a 0 over here, because that means the image is equal to the kernel, and the kernel is 0 because it's injective. So we've defined an injective map from script A to script B. One does have to be a little bit careful, though. Just be careful to show that what we've just defined from A into B is a morphism. So this is a morphism in the category of abelian sequences, or maybe you can say chain complexes. We need to verify. We need to verify that the diagrams commute. So what diagrams are we referring to? Well, what we're referring to is we have a morphism on the nth level. So this is Cn of U, U intersect V, to Cn of U plus Cn of V. And then you have the descending morphisms going down like this. So this is sort of boundary map. This is like a pair of boundary maps This is, we can call it the diagonal map. Let's not even give it a name. And then you have to show that if you have a simplex, right? If you have a simplex over here, and then you map it diagonally, well, if you have a simplex and you apply the boundary operator, you're applying it to sigma, so this would be the boundary of sigma. And if you apply the map going down this, well, how is the map being defined on the direct sum? You're just doing it component by component. So you're just applying it on the first component, you're applying it on the second component, and you can see that the map going like this, that's the diagonal map, so you just repeat it twice, and here you're just applying it on each component, and look at that, the diagram commutes. So you do actually have to verify that these morphisms compute with the diagram, but you can see that they do. So we have therefore just defined the map from A into B. Now we have to define the mapping from B into C. So I'll just remove this. I'll show you how that one works. The mapping from B into C. For the other one, it's so the one going from A to B, it's a little bit, I would say, more obvious. The one going from B to C is going to be a bit less obvious, but it's not that difficult nonetheless. So in going from B to C, we're going to pick something on the nth level for B, so we have to define it from Cn of U, direct sum Cn of V, and we have to therefore map it to Cn uv of x. So that's what we're going to define it. And here's the way we do it. We're going to pick a simplex in this one, let's call it sigma, and then we'll pick a simplex in that one, let's call it tau. And then the way we map this pair into here is, well, you should realize that sigma is already in U, tau is already in V, and we're just going to take these together. Now we're going to do it with the difference, and you're going to see why we need to do it with a difference. We're just going to take the difference of the two of these simplices, right? We can do this because this is a free abelian group generated by all such simplices. Sigma is in U, tau is in V, so sigma and tau are in this group, and because it's a group generated by them, we can take the difference. Now, at this point, you can ask, why do we do sigma minus tau? So here's just some questions that arise. Why sigma minus tau? Why not tau minus sigma? Or why not sigma plus tau? Like, there's lots of ways to do it. Why specifically are we doing it like this? Or you can even be more complicated. Why not, let's say, 2 sigma plus 3 tau, right? I mean, this is a free abelian group, so you can add it as many times as you want. Why specifically in this way? Well, so the answer, so this is actually arbitrary. So this is actually arbitrary. You can do it the other way around. That's fine. But why not sigma plus tau? Or why not other? So for the reason for this one is because we need exactness. Otherwise, we're not going to get exactness. So what I mean is we have to define a morphism from script B to script C so that we get a short exact sequence out of it. If we do it with the sum, it's not going to work, as you're about to see. So I'm going to show you why it works like this. But the answer to the first question, why sigma minus tau and not tau minus sigma, that will actually be arbitrary. That's just a choice. But the reason why you cannot just add them will be clear in a moment. So now the claim is that we're getting something that's surjective. And the reason is actually very simple, because if you pick something, so if you pick, let's say, a single simplex, let's call it sigma over here. So let's forget about this one. If you pick a simplex, and this simplex happens to be in U, then the correct element to map it one would be sigma comma 0. Sigma minus 0 will get mapped over there. But if, let's say, the simplex is tau, and tau is contained in V, but not contained in U, then the way you would do this one is you would do 0 minus negative tau, and then that one will be mapped to tau. So as you can see, this morphism that we have just defined, it is indeed surjective. Now the other question that's important is, okay, so we have exactness at A, the image of the incoming map is equal to the kernel of the outgoing map, and we have exactness at C. The image of the incoming morphism is equal to the kernel of the outgoing morphism. So we just have to check exactness at B. So let us check exactness at B. So we have to verify that if we look at the middle one, which is Cn of U plus Cn of V, and then we go to Cn of X, and on the left we have Cn of U intersect V, we have to verify that this is an exact sequence on the nth level. So how does one do something like this? Well, we already know that this is like the image of the incoming map on this one is equal to the kernel of the incoming map, and the same thing over here. We know that the kernel of the outgoing map is equal to the image of the incoming map. So because it's surjective. So we just have to check exactness in the middle position. So let's see what happens. Let's call this one, for lack of a better name, let's call this one F. Let's call this one G. And then we have to verify that the image of F is equal to the kernel of G. So we do it in two steps. We first show that the image is contained in the kernel, and then we do it the other way around. So if we pick something that's in the image, well, it means there's something in here. Let's say there's a sigma over here. Well, it does happen to be a little bit more complicated, because an element in the direct sum is not necessarily an image of a single simplex. It is a formal sum. But to keep it simple, let's say it's just a single simplex. The argument will generalize very easily. Then that one goes to sigma comma sigma. And then when you map it into that one, you have to subtract them. So that's actually the reason why you need to subtract, why you cannot add, because otherwise you're not going to get that, you're not going to get a 0 over here. So that becomes 0. So look at that. If you take a sigma in this chain and you apply this mapping, you get sigma comma sigma, and then when you apply G, you subtract and you get 0. So images contain the kernel. That's why you need it. And then you consider something a little bit more general. What if this element is a formal sum of simplices? Well, then you just apply it on each simplex in the formal sum and you get the same result. And now you want to do it the other way around. You want to show that the kernel, you want to do this. You want to show that the kernel of G is contained in the image. So you kind of do the same thing as before. You say, let's say there's something in here that gets mapped to 0. Now, whatever that element is, it's a formal sum of simplices. So to keep it simple, let's say it's just a single such simplex, and then you have to consider the more general argument. But if you have like a single such simplex, if you have, let's say, sigma comma tau, right, and G maps these two into, so this becomes sigma minus tau, and this becomes 0. Well, if it becomes 0, then what does that mean? It means sigma is equal to tau. Sigma is equal to tau. So then this is just sigma, right? You can just make that sigma, and then you just map sigma to, and then you have the diagonal map. These are exactly the same. So in particular, sigma is contained in the intersection because it's in U and it's in V, right? So that's what you have. So the result follows. So we have a short exact sequence coming from here. Of course, you do have to check that those squares commute that we said from before, but that's not difficult to check. So we have the short exact sequence, and now we apply the zigzag lemma. And now we're going to apply the zigzag lemma, and we get an exact sequence, in homology. So the way this is going to go is we can calculate the nth homology of A, the nth homology of B, the nth homology of C, right? This is what we get in the zigzag lemma. But then furthermore, we have the descending map that returns us back to A. So that's the zigzag, and then we go across, and here we have Hn plus 1 C, and so on. So this is what we get. This is our exact sequence in homology. And now let's just work this out a little bit. So let's start with the easiest one, and that's A. So the homology of A. Well, if you look at A, script A, that's just the usual chain complex. It's just the homology arising from that chain complex of the intersection. So by definition, the homology that you calculate using this chain complex, that's just the homology of this topological space. So this A over here can just be replaced by H n U intersect V. That's just the homology of the intersection by definition. Now, what do we do with the one with the B? Well, let's look at B. B is, it's a chain complex that you get for U, direct sum the chain complex that you get for V. So this is not difficult to check. And in fact, I'm going to put this on the homework, but the homology that you end up getting for B is going to be isomorphic to the homologies of each of these two individual homologies you get for the two separate chain complexes. So this one is just going to be isomorphic with H n of U plus H n of V. So the homework exercise is going to basically say this: the homology of a direct sum of chain complexes is isomorphic to the homology, to the direct sum of the homologies of each chain complex. This is very, very easy to show, but it has to be said. Basically, if you're confused, like what are we even trying to say? What I'm saying is, look at B. How are you constructing B? You're using the chain complex on U, and you're using the chain complex of V, and then you're getting a chain complex on the direct sum by using the boundary operators for U and V separately. So that's how you're creating a new chain complex. So the homology of this new chain complex, which is formed by taking the direct sum of those two chain complexes, the homology that you get for that new chain complex will be isomorphic to the homology that you get for the first chain complex, directed sum with the homology you get for the second chain complex. That's basically what we're saying. That is not difficult to check whatsoever. But it does require verification, and if you verify it, this is what you get. And now the part which is the trickiest is this C over here. And now we have to just understand what C is. I think it would be helpful to do it down here. It's just, okay, so I want to just say this. So Cn of script C, this is the homology. Well, you have to say what this is the homology that you get. Well, maybe we should say what script C is. So script C, these are chain complexes that you get where the nth group is the free group generated by all simplicities that sit in U or V. And let's say we create this one, let's call this one D. This is just the chain complexes of X. Now, if we calculate the nth homology of D, this is just by definition the nth homology of X, right? How do we find the homology of a topological space? We create these groups of chain complexes, and then we compute the homology that we get from that chain complex. But this one is something that's a little bit different. This is what we want to do. We would like to be able to replace this by H n of X, and to replace this one by H n of X. That's what we want to do. Right? This is what we would like to do. The problem that arises here is that this chain complex, as you can see, this is not the homology of a topological space. This is like some kind of restricted type of homology. And this is going to be the technical result that we're not going to prove. This one takes a lot of pages to prove. And when I say a lot, I mean a lot. It goes on for pages and pages and pages and pages. There's lots of things that one has to check. This is very technical. So what I'm about to say, this is called, the name of this result is called barycentric subdivision. I guess lemma, I'm not sure what to call it. So this is very, very technical. When we write it down, it's going to make a lot of sense. It's going to be very believable. It's like one of those things that it's not some kind of unexpected result that bothers you, that it's difficult to accept it and keep on moving forward. This is going to be one of those things that just feels completely true. But then to actually prove it carefully, that's when it gets unbelievably tedious. So this is very, very tedious. And it says this, that if I guess there's like maybe two parts to it, but maybe we can call this maybe like part one, perhaps. And it says this, that if, let's say we have a chain C in, I'm just going to do it in one shot. That if, let's say script C, so this is going to be a homology class, is a homology class in Cn of X. So in other words, the C is a formal sum of simplices in this one. Then this representative C can be written as A plus B, where A is a chain. So I guess there's a part, so barycentric subdivision, it's a lemma with two parts, where you can decompose the chain, your cycle, right, your cycle, in this way, so that A, no, that's not what I meant. Let me take it back. So then we can find an A in H A in C N X, let's say U. So this one, it means exactly what this one means, except, well, I mean, there's no need to, I mean, we can probably just write Cn, we can probably just write this Cn of U like that. If you prefer, if that bothers you, you can write Cn of X U like this. So it's the chain in X that's contained inside U. And of course, whatever this is contained in Cn U comma V of X. So we can find an A and we can find the B in the other one. So this would be Cn of V of X, which is contained in Cn uv of X, such that the homology class of C can be represented as a sum of these two. It can be split. And furthermore, so I guess there is a part one and a part two. So this is like part one, and then part two will follow from part one. And furthermore, the homology that you get for D is actually the homology that you get from C. Now, if the moment I draw pictures, this will make it be very believable. So here's what we're saying. We're basically saying this. We have these two different homology groups. One of the homology groups, so this D over here, that's the homology that we want. That's the homology of our space. Script C, this is a restricted type of homology, where your simplices are either in U or V. And here's what we're saying. So here's the picture that goes along with barycentric subdivision. So here's what's happening here. your space decomposes as a union of two open sets. Now, you have a cycle. It's a cycle. So let's say, so this C is some kind of cycle. If your cycle, maybe I'll draw a solid triangle. It does not really matter. But in this case, the cycle is completely contained in one of them. Let's say this is U. So it's completely contained in one of them. And this is what we're saying. The cycle can be written as a sum of A and B, where one of them is in U, one of them is in B. So in this case, the cycle is already in U. So you can say the cycle is equal to, let's say, C plus 0, because the cycle is already in U. Likewise, if it's on the other side, right, if the cycle is over here, let's say, right, so let's say this was your cycle C. I know the way I'm drawing it, it's not a cycle because it's supposed to have boundary 0 if it's a two-dimensional simplex, but it's just a picture. Then you would make A be 0, and then B would just be C itself, and then you have decomposed C in such a way. But the complicated thing that happens is, what if the simplex falls into, it spills over into both of them? Right? Let's say your simplex, I'm drawing it as a square, it doesn't really matter how you draw it, but let's say your simplex, it spills over, your cycle, it spills over into U and V. Then this is why it's called barycentric subdivision. The idea is you just triangulate this simplex further. You just triangulate it further into smaller pieces, and if you make it sufficiently small enough, then you can do it in such a way that this part you can then call A, and that part you can just call B. You just triangulate it sufficiently small enough so that the smaller simplices that make it up are now contained in U and V. So this is the part that actually requires technical justification. And this is why you need the sets to be open, by the way. Because if the sets are open and the overlap, then that means you have just enough space to move around. And by making these subdivisions sufficiently fine, by making them sufficiently small, you can be contained entirely in either U or V. But here's the problem. The problem is that C is not equal to A plus B. Because, well, I mean, just to keep it very simple, if C is this, and then you break the path into two paths, A and B, you cannot say that C is equal to A plus B. Because by definition, C is a mapping from a single simplex into your space, whereas A and B, this is two separate mappings being put together as a list. This is, after all, a free abelian group. So C will not be equal to A and B. And this is why I'm not saying C is equal to A and B. I'm rather saying the homology class of C, the homology class of C, because the homology class can be represented by different representatives. So, and what we're saying is that even though C itself is not equal to that, the homology class, on the level of classes, it would be equal to A plus B. And so the point is, and this is the whole point of what we're doing, is that you can replace every, right, so every cycle, let me remove this. So so basically what part one is saying, every n cycle can be replaced. So when we say replaced, we mean homologous, right? When we talk about homology, we talk about n cycles up to homological equivalence. So every n cycle can be replaced by an n cycle, so that all of its components, I guess components, but you would say all of its summands, right? Because a cycle is a formal sum of simplices, so these are the simplicial maps, right? The simplex maps, the summands, that's what they are contained, are in U or V, one or the other. And so what this shows is that you can assume that all of your cycles have this special form, that the cycle itself, it comes from chains that are living in U or V. And so it means that the homology that you're getting on the entire space is actually arising from this restricted type of homology, right? The homology that you're getting on the entire space by considering all simplices, you can just get it back from this more restricted type of homology where you have special type of simplices which are in U or V. And that's the main idea of what we call barycentric subdivision, that even though it's a different type of chain complex, when you compute its homology, it actually returns back the original homology. You're not losing any information. And that's what we're saying. And so because of this, the barycentric subdivision theorem tells you that you can just replace this by hn of x. And that's what you get. And this is the Meyer-Vittora sequence, the exact sequence in homology. And this is what we're going to be using to help us compute homology of various spaces. So before we finish, and maybe I should just make a remark about this. This is unbelievably tedious. You can look at the way Alan Hatcher proves it, for example, even though, as I remarked, Alan Hatcher does have a tendency to leave out as many things as he actually writes. And if you look at the way he proves it, he first has to develop something called relative homology, which we're not talking about, and prove various properties about it. Then he has to talk about barycentric subdivision. Then he has to show that these things work out in the end. So it's an unbelievably tedious proof if you're doing it very carefully, but I think it's very believable. It does make a lot of sense. It's not like one of those things that is difficult to accept. This one makes a lot of sense intuitively. So it's easy to accept it and use it. And I think when you're first learning homology, you're just trying, I think it's more important to learn how to do the calculations and think about it before you start proving everything else. So let's just summarize the Meyer-Vittora sequence, and then we'll be done with this. So here's how we summarize the Meyer-Vittora sequence. Let's call this a theorem. X be equal to the union of two open sets. We have the following exact sequence in homology. And it goes like this. Hn of x, the n homology of x, can be mapped into the n-1 homology of the intersection. That gets mapped into the hn-1 homology of u plus hn-1 of v. This gets mapped into hn-1 of x. This one, the one before that, this is hn of u plus hn of v. This is hn of u intersect v, hn plus 1 of x in there, and so on. So we have this, this is an exact sequence, and it's an exact sequence that relates the homology of x with the homology of u and v and the homology of the intersection. It would be helpful to also discuss how these mappings work, because sometimes we need to use these mappings. So let's talk about how these mappings work. So the easiest one to first talk about is, I mean, this one and this one is the same thing. This one's just nicer because you have n instead of n-1. So let's talk about how this one works. So the way this one works is that if you take something in the homology class, so let's say you have a cycle C, so that's in the homology class of the intersection, then you map that homology class diagonally. So this is the homology class of C, and then you have the homology class of C again. You just want to be careful that this is not necessarily injective. It could be, but it does not need to. It's just a trick of notation, because it looks like C is being mapped to itself, but it's not really being mapped into itself, because this is the homology class with respect to the intersection, whereas this is the homology class with respect to U, and this is the homology class with respect to V. What you're basically doing is you're saying that U intersect V, it injects into U, so that means the homology of the intersection, right? If you have, let's say this is I, then that induces I star, and that's the induced map on homology, the induced homomorphism on homology. Well, this one could be injective, but as we've talked about before, the induced mapping does not need to be injective. So it does not need to be injective, because the point is that maybe C is not homologically trivial, but because you have U over here, which is a larger space, maybe the inside of C, which is empty, it could be filled in the larger space, and so this becomes homologically trivial. So it just looks like it's an injective, but it does not have to be an injection. So we do want to be careful with this, but this is exactly how we're getting this map. Now, that's this one explained. What about this one? So this is the one that we talked about. If you have, let's say, a homology class C1 for U, and you have another homology class for another cycle C2, then the way you map that pair is you map it by subtraction, and you have to make a choice about which one is first and which one is second. So you do C1 minus C2. That's the way you do it. So this square bracket now represents the homology class in X. So this was the homology class in U. So we're kind of writing the square bracket again, but we have to, I mean, we are mature enough to understand this has to be the homology class in X. So you just do it with subtraction. So this is the difference map that we've talked about. And now the one that's the trickiest is the one that lowers the dimension. This is the one coming from the zigzag lemma. So this is the trickiest one. This is the lowering of dimension map. So some people call this the boundary homomorphism. Some people actually call this like delta star, sort of like the boundary map, but induces a homomorphism. So it's the boundary homomorphism, and it's going to use barycentric subdivision, as we've said before. So here's the way that it works. We did talk about barycentric subdivision just a few moments ago. So here's the way that it works. You're going to pick a homology class. You're going to pick a homology class in X, and you're going to replace that homology class as a sum. Right? So C is going to be a homology class in X, and you're going to replace this representative by A plus B, where A is a chain. This is a chain. A is a chain in U. So this is actually an n chain in U, and B is an n chain in V, right? That's barycentric subdivision. By the way, I'm being extra careful. I am not writing A plus B. The reason why I'm not writing it is because A by itself is not necessarily a cycle. It's just a chain. Together, they give you a cycle. To give you a very simple example, like, so look at this circle over here, right? This is a cycle. So you can kind of break it into two pieces. This is A, and that's B. So A plus B. So we're not saying A plus B is equal to C. We're saying the homology that you get from the sum of those two will be equal to the homology class that you get for C. So you can replace the homology class as the sum. But individually, you cannot talk about the homology class of A by itself. That does not make sense because this is no longer a cycle necessarily. So that's why you have to keep it together like this. But by barycentric subdivision, you can replace anything in X, right? This is what we were saying, that any homology class of a cycle in X can be replaced so that it's in this sort of restricted type of homology. And then, how do you go from this one to this one? So how is this map? So how is this map being defined? So this lowering of dimension map is being defined by the boundary operator. So after you've written it in this way, you're going to apply the boundary operator to lower the dimension, and you're going to apply the boundary operator to the A component, to the one that's in U. So this is going to be boundary of A. That's what you replace it by. It's going to be the boundary of A. You apply it only to the A component, not the B component. Now, if you're confused why the A one and not the B one, well, it has to do with the fact that the map that goes from this sum into X, you have to make a choice about which one is being added and which one is being subtracted. And this choice then forces this choice in order to have an exact sequence. So basically, so maybe I get rid of this. So I'll do it like this. We're basically saying this. We're saying that you have your cycle in X, and this cycle is homologous to A plus B. And then the way you calculate this map is you're going to apply the boundary map on the first piece. You're going to do boundary A. Well, what if you do it? What if you use the other piece? Well, you see, because C is homologous to the sum, it would mean that this would be homologous to A plus B. But this is going to be 0 because C is a cycle. And so what we're getting is that the boundary of A would be homologous to negative boundary of B. And if you're going to use the other one, you can use B. But if you use B, then you have to use it with the negative sign. This all has to do with the fact that, like, you need an exact sequence. So we're saying this. If you have, let's say, like C1, I'm going to be sloppy. I'm going to write it without square brackets. So you just subtract the two, right? You just subtract these two, right? This one, you subtract them. But then how do you then map How would that, so if you subtract them, but how do you then map it in here? Well, because C1 is the one that's in U, you're going to apply the boundary operator to C1. So that would be the way you have to do it. You can also apply the boundary operator to C2, but then you have to do it with the negative sign so it's consistent, because, right, then you have to do it with the negative sign and then it's consistent with that. So it's because the arbitrary choice that you're making about which one is first and which one is second has to then force the way this map is defined. Do you apply the boundary to the first, to the chain that is in U, or do you apply it to the chain that is in B? I'm sorry, that is in V. So that's what you have to make that choice. But now that we have this, so let me just maybe explain again how this works. So you pick a cycle. So you pick a cycle over here, and then you replace that cycle by a homology class A plus B, where A is contained in U and B is contained in V. Okay, and then the way you map this is you apply the boundary map to A. And the moment you take the boundary, you automatically get a cycle. So even though A itself might not be the cycle, the boundary operator will lower the dimension and it will give you a cycle, right? So you're now getting a cycle of dimension n-1. You might be wondering, why is it in the intersection? How do you know it's in the intersection? We only know at the moment that it is in U. Well, that's actually very simple. That goes back to what we were saying earlier, that if you take the boundary of that sum, you get 0, because this is homologous to C, and C is a cycle, it becomes 0. And so that would mean that the boundary of A is minus the boundary of B. Or if you prefer, the boundary, yeah. So the boundary of A, it is in U, and because it's negative boundary of B, B is in V, so its boundary is also in V, so it's in both. So this is how this map is being defined. This is the trickiest map, but that's the way that it works. It's basically the one that comes from barycentric subdivision. So this is how all of these maps are defined. This is the Meyer-Vittora sequence. The zigzag lemma tells us this is a exact sequence in homology, and this is going to be the setup. So in this lecture, so today's lecture carefully develops the sequence, and in the next lecture, we will assume this sequence and use it to compute homology of various topological spaces. So you will see it used, you will see how you actually use it to compute homology for you. But that's enough for this lecture. We'll finish here, and then next time you actually get to see some nice computations of how you actually use this result to compute homology groups.